Hello everyone, welcome to Tech-Lavya. Please like, share and subscribe.
Now students, the topic for today's class is the open circuit test for transformer. That is also known as OC test or no load test. Fine. So we shall talk about it, and let me tell you that this topic is very important for our examination. Now we have already discussed no load condition, isn't it? So what was no load condition? The secondary side was open circuited, and we said that yes, in this condition no load current flows through the primary, which we represented by I naught. Correct? Okay. And we also saw that under no load condition, why no load condition is used? Now no load condition was basically used to find the core loss or iron loss. Okay. Sorry. So no load test is basically an experimental setup to find out the core loss. Okay. So basically the aim of this test is to find core loss. Now in addition to find core loss, in addition to that, we also find equivalent core loss resistance, magnetizing reactance and no load current. How are they represented? Core loss, the core loss is represented by Wi. I stands for iron loss. Correct? Equivalent core loss resistance stands for RO or R naught. Similarly, magnetizing reactance is represented by X naught, and the no load current is represented by I naught. Please keep these things in your mind that we are going to find all these parameters. Okay, so before going to the actual diagram, I would just tell you how you can remember, the diagram. Okay, because ultimately when you see the ready-made diagram, you might feel that no, it is difficult to draw, but actually it is quite simple. Okay, correct? So here we have a setup. Fine. Then we connect a voltmeter here, and here we have auto transformer. See, the word transformer has a shortcut form. I mean, we technocrats or engineers use this. Okay, we write X and superscript MER. So this represents transformer. Okay, yes. So here we are going to supply AC, which is V1. Now, what is the meaning of this portion? That we are going to vary the signal. Okay, remember we represent the rheostat by this. Correct? Similarly, that is auto transformer, so that we can vary the signal. That is also called known as variac, variable AC. Fine. Yes. So now here we have voltmeter so that we can measure the voltage. Now why it is required, we'll discuss about it later. Then we have a wattmeter. Why do we have a wattmeter? Because we need to measure the watt, which is Wi, correct? The power. So this wattmeter will give you core loss or iron loss. Fine. After that, a current flows, which is I naught. So we want to measure this also, right? So here we will use an ammeter. Finally, this goes to transformer, primary. Okay. See, after this, we know that this is open circuit test. So output is open circuited. Fine. Okay. So this is how the diagram has to be drawn. Isn't that simple? Now you know what all has to be, measured. So simply you have to incorporate those devices here. Fine. Now another important point which you should remember is this side is called LV side, that is low voltage side, and the secondary side is called high voltage side, for the simple reason that the secondary is open circuited, right? So it is assumed to have a very high voltage. Okay, so here the secondary side is high voltage side and primary side is low voltage side. Now please remember, in open circuit test, the high voltage side is open circuited. Okay, and low voltage side is given supply. Fine. So basically this is the setup. Okay, now what I'll do is I'll erase this and yes, now see, this is how the circuit looks like. Both are the same circuits. Okay, so here high voltage winding or side is open circuited, then supply is given to the low voltage side, that is LV side. Wattmeter, voltmeter and ammeters are connected in the low voltage winding or the primary winding. Now here rated voltage is applied at the input. Please remember this. Rated voltage is applied at primary, okay, which is low voltage side. Fine. So rated voltage is applied at the primary. Now flux is set up in the core. So we have iron losses. Fine. These iron losses will be read by wattmeter. So directly wattmeter is going to give us iron loss. Secondly, now we know, since it is a no load condition, the primary no load current is very small, but again that is read by ammeter. But since here the no load current is very small, the copper loss is negligible. So whatever reading our wattmeter gives actually corresponds to core loss or iron loss. Okay, because copper loss is negligible. Fine. Now, why do we require voltmeter here? We are not measuring the voltage as such. Well, voltmeter is required because see here what I have written, that rated voltage is applied, right? So continuously I'll be changing the voltage till my voltmeter shows me the rated voltage reading. Suppose rated voltage is 200 volts. How will I come to know that 200 volts is getting applied to transformer? So continuously I am varying this, isn't it? So I am varying this point and I will vary this till this voltmeter shows me 200 and then I will stop. I will not touch that. Okay, and then corresponding wattmeter readings and ammeter readings are taken. Is it clear now? Yes? Okay. So this is how the phasor diagram looks like. Now the same phasor diagram was discussed under no load condition also. So we will not be discussing it in detail, but then this is a flux which is set up by the application of the primary voltage. Now this set flux is in lagging condition with respect to V1 by 90 degree. Then we have the no load current which has two components, IM and IW, and the resultant of this is I0. And this phase diagram is represented by phi naught. Right? Correct. So what all readings do we get? The wattmeter gives you the iron loss. Correct? Yes. So we get the voltage and the current. We can calculate the power factor, isn't it? Because how did we get that? Because this is represented by, we have seen these equations in earlier classes. So it was V0 I0 cos phi. So since my wattmeter gives me W0 and I'll get I0 and V0, so I can calculate cos phi naught. Okay. So the core loss component and other values are shown here. Fine. Okay. Now the reactance will be current upon the reactance will be voltage upon current. Similarly, the resistance will be the voltage upon current. Correct? Yes. So here, just 1 second. This is basically, this is IW. Okay, this is IW. Yes. Otherwise, all the things are right. Yes. So the resistance is based on the working component and the reactance is based on the magnetizing current component. Fine. So see, you must be wondering that why these values are written. Now, when we will solve the numericals, no, there we will be requiring these equations. So please remember, okay, that you get the iron losses in no load or OC test. Okay, and this is represented by V0, I0, cos phi. I0 has two components. The working component is given by I0 cos phi. The magnetizing component is given by I0 sin phi. Then you have the magnetizing branch reactance, which is given by the voltage upon the current. Similarly, you have the resistance, which is given by the voltage divided by the corresponding current. Now see, we can interchangeably use Im or I mu. Okay, they are the same. Fine. So what did we learn today? Today we learned that in open circuit test, high voltage side is left open. The rated voltage is applied at LV side, that is low voltage side. Now this applied voltage is responsible for the iron loss, which is measured by the wattmeter and it is represented by W0. Secondly, because of no load condition, no load current flows through the primary, which is negligible, and hence we can say that copper loss is negligible. Fine. So with this we end today's lecture. We shall meet in the next lecture with short circuit test. Thank you.